wanted to work through an example involving light. It's a problem that involves our understanding that light, an electromagnetic wave, carries energy and momentum, that light transfers energy and exerts forces. And in this problem, we're going to imagine that we are levitating or supporting a reflective disk, 100% reflective disk, by a laser beam to counteract the gravitational force. There's an upwards of force exerted by the light, by the laser beam. So in this particular question, we're told that the laser beam levitates a 100% reflective disk that has a mass 5 grams and has a radius 4 centimeters. We're imagining the laser light is shone upwards on the disk. It's reflected off the disk. This causes a radiation pressure on the disk, causes a force on the disk, and that's going to help us support the disk. Now, in my picture, I've just drawn a ray of laser light bouncing off the disk, but actually we're going to imagine that the laser light is distributed over the entire surface of the disk. So it's a beam of laser light, the size of the disk, that bounces off the disk. Let me add to the sketch. Let me annotate the sketch with some information, some understanding about what's going on. We've got a gravitational force on the disk that's pulling the disk vertically downwards. I'll indicate that as Fg. And we're exerting a counteracting upwards force on the disk. It's the force of the laser light on the disk. I'll call that FL. And these two forces are equal in size, they're opposite in sense. That's how we're supporting the disk. And so that's the basic idea of the way that we're levitating the disk. There's some numbers we know, as I mentioned. We know the mass, it's 5 grams, or 5 times 10 to the minus 3 kilograms. We know the radius of the disk, I denote that R, is 4 centimeters. And so we could calculate, for example, the area of the disk on which the laser light is shining and supporting the disk. So my starting point in solving this problem is this basic idea that the gravitational force downwards is being counteracted by the laser light force upwards. They're equal and opposite. And I'm going to start worrying about the sizes of the two forces and the fact that the sizes of the two forces are equal to one another. So FL, the magnitude of that force, is equal to Fg, the magnitude of the gravitational force. Now, the gravitational force we know we can write as the mass of the disk times the acceleration of gravity on the disk. And the laser light force, well, we could first write it as the radiation pressure of the laser light times the area over which that laser light is distributed. That's the area of the disk. And then we could expand this a little bit. So we could expand the radiation pressure in terms of the intensity of the laser light. I could write it as 2I over C. That's the radiation pressure exerted by laser light of intensity I if it's fully reflected. If it was laser light that was fully absorbed, the radiation pressure would just be I over C rather than 2I over C. But our laser light is being fully reflected. And then that factor multiplies the area. The area is the area of the disk, it's pi r squared. So at this point, we've built for ourselves an equation that contains the intensity, which is the quantity that we want to figure out, in terms of other quantities that we either know, because we're told them in the problem, or we can remember, because we happen to remember them, or we can look them up. So the expression for the intensity if I multiply through by c, if I divide through by 2 pi r squared, is this equation here. And so the mass of the disk we're told in the problem, the radius of the disk we're told in the problem. C, G, they're two parameters. They're two quantities. They're the acceleration of gravity, the speed of light. We know those. We're going to look up those. And then we've got a factor of 2 pi. So all I need now to do is to stick in the numbers into the equation. So let's walk through this. There's the speed of light, 3 times 10 to the 8 meters per second. There's the mass of the disk. I've got to put it in SI units. So it's 0.005 kilograms. Then there's the acceleration of gravity. We all remember that. That's 9.8 meters per second squared. And then we've got to divide that by 2 times pi times the square of the radius of the disk. The radius of the disk was 4 centimeters, or 0.04 meters. And if we go ahead and calculate this quantity, I've already done that, I just need to look it up here. It was 1.46. It's 1.46 times 10 to the 9 watts per square meter, or just 1.46 gigawatts. A gigawatt is 10 to the 9 watts per square meter. So that's the intensity. What you see here is that although in principle one could support or levitate a disk, a metal disk or a reflecting disk with laser light, the challenge, the difficulty is that in practice, the intensity of the laser light to support, levitate the disk is enormous. We need laser light with an intensity of 1.46 billion watts per square meter. That's a very, very, very intense laser light.